Good afternoon, everyone. I'm Lei Han. I'm from Rutgers University. And this is a joint work with Dr. Yu Zhang and Professor Xiufeng Wang and Professor Tong Zhang. And our topic is about the generalized hierarchical sparse model for arbitrary order interactions and its application in flow various data. I will first introduce some background of this work. And some recent statistical results have shown that incorporating the interactions among the original features can improve the interpretability of the biological data. And a typical example is the problem of the antigenicity analysis for the influenza virus. And actually, in this problem, each virus has some protein sequence. And the sequence may contain many amino acid positions, which can be viewed as the original features. So each position can evolve and mutate to some new amino acid. So when this happens, a new variant of the virus will come out. So for example, in the figure, a virus A, after some mutations, it becomes a virus B. So they want to know whether the virus B is a new variant of in the literature. So the main concern here is that multiple mutations at different amino acid sites can mutate at the same time. So this can significantly enhance the probability of the antigenic drift. So discovering the interaction pattern here is very important for predicting the antigenicity of the new viruses. So many existing approaches haven't taken into account of the second order interactions and proposed some interaction model. Generally, they consider a linear regression model like in this equation, and it contains the first part is the original feature part. It's a regressor with some weight beta I. And the second order interaction part is the second term that here we mean the second order interaction, we mean that it's a element-wise product between the original features. So this is just a simple linear regression model to involve both the original and second order interactions. And here D is the number of features, and this symbol is the element-wise product between vectors, and beta I is the coefficient for the original features, and phi ij is a coefficient for the interaction term for ij. Okay, so when we consider an interaction model like that, we may prefer to introduce some sparsity for the model coefficients. This is because the number of the interactions is much larger than the number of the original features. So actually, the simplest way to apply sparsity is we can use the lasso method, which we can treat all of the features equally. I mean, we treat the original and the interactions equally. But this way fails to include some logical heredity relationship. That is because the interactions are actually generated from the original features. It's an element product between a pair. So in order to take advantage of some logical relationship, some statisticians have devised some heredity structure here. For example, commonly, two types of commonly used heredity structure are the strong heredity and the weak heredity. And for the strong heredity, it's easy to be understand is that if a second order interaction is selected by the model, it means the coefficient phi ij is non-zero, and then both of the corresponding original features must be included as well. So that means both of their coefficients should also be non-zero. And the weak heredity just make a relaxation of this relationship, and it changes the and to or. So it's a relaxed relationship. And actually, both the strong and weak heredity have been well studied. For example, Ben Taylor and Tiprani proposed two hierarchical sparse models, and one just applies the strong heredity here, and another corresponds to the weak heredity here. And in these two objective functions, they use a inequality constraint to achieve this heredity structure. Here, for example, they force the absolute of beta I should be larger than or equal to the L1 norm of the second order coefficients. It's because if the beta I is 0, and this part should be smaller or equal to 0, so it must be 0. So it just can encode this relationship. Also, some similar approaches considering the same heredity structure like the one-ish model, Regression model family, and Shim model works in a similar way. And many of the second-order interaction models have been proposed. But unfortunately, all of the existing approaches consider at most the second-order interactions. And solving the higher-order interaction model is very challenging. This is because when we consider higher-order interactions, the number of the interaction term increases exponentially. That is, when, for example, when we consider kth-order interaction terms, there will be a combination number CDK here for the number of the kth-order interactions. So it increases exponentially just according to the order we consider. And moreover, for high-order interactions, the heredity structure among different orders will become much more complicated. So in this paper, we just aim to solve this hard problem, and we aim to include arbitrary order interactions. So for example, when we consider up to the kth-order interaction, this regression model can be formulated as in this. It's the linear regression model. And the first, for example, the first part is also the original features, and second, we involve the second order, and so on. And at the kth order, we just involve a linear regressor of the kth order interactions. But note that here we use a partial ordering of the index for each interaction term to avoid redundancy, because the interaction is unique given the index, and it's not related to the ordering of the index. So this is also why the number of the interaction is a combination number. Okay, now intuitively, if we just follow the concept of the strong and weak heredity for the second order case, we can get a straightforward extension, for example, for the strong heredity for the arbitrary order case. And this can be given in this equation. That is, if the kth order interaction coefficient is non-zero, then all of its related k-1 order interaction should also be non-zero as well. But there's a problem. It's that this above definition is an element-wise definition because it works on elements, each coefficient. This will lead to a very large number of constraints. It's a sum of a total combination numbers. This is intractable to be solved for many real-world problems. So in order to address this issue, we propose to give a new definition for the arbitrary order case. This is what we call arbitrary order heredity here. And in this definition, we define that if an entire vector of the kth order interaction term is a zero vector, and here this EI vector means this is a binary indexing vector that can indicate the interactions which include the original S feature. So if the kth order interaction vector is zero, it must be that the higher order interaction terms, the entire vector should be zero as well. So in this definition, it defines that if an entire vector of the kth order interaction, which includes the original feature I, is zero, then the relevant higher order interaction will also, yeah. So I'm sorry. If none of its associated kth order interaction term is contributed to the regression model, then neither do its associated higher order interaction. So this makes some sense. And one benefit of this definition is that this definition poses a constraint on sets of variables instead of the individual coefficient. So it only leads to a small number, k-1d constraints, which is much smaller than the previous large number here. And so here is an illustration of the relationship of the among among the strong, weak heredity for the second order case and our proposed arbitrary order heredity. And one thing need to be mentioned is that the strong and weak heredity contains some redundancy, since different ordering of the index have different variables in their model. For example, the interaction 1, 2, and 2, 1, they treated them as two different variables. But in our arbitrary order structure, we remove this redundancy and gives a more compact definition for the relationship. And now, based on our definition, we propose our generalized hierarchical sparse model here. And the formulation is given here, where L is a loss function that is based on the previous regression model. And the second part is a general L1 regularization, and we can also put the tuning parameters here to allow them to vary according to the orders k. And the most important part here is this chain, like a chain inequality constraint. In this chain inequality constraint, it makes sure, for example, if the first order is 0, then we have a second must be 0, and the higher ones must be 0. So this chain constraint here just can satisfy our definition. Okay, now we want to solve this problem. Let's take a look at this problem. First, it's non-convex, and second, it has a complicated chain constraint, and the variables are also coupled in different chains. So this problem is hard to be solved. And in order to solve it, we then developed a very efficient optimization method, which is also a main contribution of our work. I will show some algorithm sketch here. The algorithm first uses the GIST method. It's general iterative shrinking thresholding. It generates some proximal step. Then this is a subproblem becomes much easier. But still, the chain constraint also exists here. So we then use the ADMM method to decouple the variables, and finally we can get 3 subproblems here. And the key technique here is that we show all of the 3 subproblems admit some analytical solutions. For example, it's easy to see that the first one can be solved by non-negative thresholding, and the second one is a general QP problem, and the matrix H is positive definite, and it has a low rank plus diagonal structure, so it can be solved in a closed way. It will be very efficient. But the third problem, which still contains the chain constraint, is much more harder to be solved. Actually, we further show that the third problem also admits an efficient analytical solution. We found that it has several very interesting properties, and these algorithms allow a OK time to solve this subproblem, where k is the number of the orders. So I will skip some details of the theorems. If you're interested, we can talk about it later. So, and moreover, all of the subproblems are independent with each other, so they can be further parallelized. Okay. So with the above proposed method, we now ready to show some experiments. We compare our method with a large number of the state-of-the-art sparse interaction models. This include the general lasso method and the all interaction lasso, which means we treat all the features equally. We just apply the lasso method to it. And the weak heredity net, and efficient weak heredity net, strong heredity net, and a family model, both all of the 4 models are the second order interaction model. And last, we just shorten our method as GHSM, this generalized hierarchical sparse model. The dash k means we can treat any order of the interactions. This table gives results on some synthetic data. And in this toy data, we simulate a number of 20 features, and we consider up to the 5th order interactions. Although the number of the original features here is small, it's only 20, but we see that the number of the higher order interactions is large. And this big table reports the recovery of the non-zero elements in terms of the sensitivity and the specificity, and also the mean square error. And we found under various simulation settings, the higher order interaction model always perform better than the lower ones. So this just gives a validation of our assumption that the higher order interactions should be important. And next, we focus on the problem of the virus antigenicity analysis. We use the H3N2 influenza virus dataset. This is a problem we introduced at the beginning, that the multiple positions in the virus sequence can change, can mutate at the same time. So in this data, there are more than 300 original features, and the number of the interaction terms is extremely large here. So this table gives a statistic of the data. And the bottom table reports the mean square error, and we found that the models with, also similarly, the models with higher order interactions always perform better than the lower ones. And in this case, we consider up to the fourth order interaction, and this model is the best one. Also, in addition to the performance measurement like the mean square error, we want to visualize how the prediction result is good. So we can just in the influenza virus analysis, there's a simple way to show the visualization. That is, we can use the multi-dimensional scaling method to plot the variance onto a 2D or 3D space. And in these 8 figures, the first one is the ground truth, and each point denotes a virus. And the virus are colored according to different years. We can see a different grouping structure here. And the rest figures are the prediction results from different models. And we can see also the higher order interaction model gets much clearer, much better recovery results. Okay, finally, there is a case study that when we selected the higher order interaction, we labeled some important features here. And we also found that all of the selected features are located at the surface of the protein structure. It's more like a hand or surface of a virus. So it has been biologically found that these regions are more likely to be active during the reaction experiment with some sera vaccine. So they will be much more active. So this just matches our numerical results. And at last, we also compare the running time of each method, because we claim that one of the important contributions is the algorithm, optimization algorithm. And this is a running time comparison table. And our methods show very fast speed. For example, in this entire influenza virus data, for the second order, because we can generalize the second order model, we only use 20 seconds. And when we increase the order of the interactions, for example, the third order, the fourth order, it's still very fast. So it do not increase very significantly according to the number of the orders. So it's just validates that the scalability of the method is also good. Okay, now I will make a conclusion of our work. In this work, we first generalized the hierarchical sparse model to deal with arbitrary order interactions. And then we developed a very efficient optimization algorithm to solve this non-convex problem. And in the experiments, we take into account of the hard influenza virus analysis problem, and we show the effectiveness of our method in this data set, and can provide many biological meanings for the experts. So for future work, one of the future work is that when we consider high order interactions, an important issue is still that the number of the dimensionality is very high. So we want to involve some dimensionality reduction techniques, such as feature screening, typically for this sparse model. And we are also interested to apply our method to other applications, such as the cancer data or macro data analysis, where the features can have some complicated heredity relationship. Okay, thank you. Thanks for your attention. Question?
So any questions? We have time for several questions. Okay.
So in experiments, did you find some examples that the higher order interaction influence the result very much than the lower order interactions?
Yes, actually, in this case study problem, here the labels are some selected features from the higher order patterns. I don't copy the interaction pattern here, but it's in the paper. The details of all of the interaction patterns are in the paper. Maybe I can show you the detailed interactions there. Yeah, there are also many meaningful third order interactions or fourth order in this problem. It's many commutation pattern. Yeah. Okay. Thank you.
One more. Okay.
So when you model interactions, is it necessary that they should be in a multiplicative form, element-wise multiplication, or it can be some arbitrary functional form for the interaction?
You mean other
should it be like x1, x2, x3, or can it be like x1 squared plus x3 squared or something like that? You know?
Yeah, it's applicable. You mean, I'm sorry, because most of the important part is the regularization part and the constraint part. So the function can be, you can choose some like different problem like classification and regression. You can choose different loss functions. Yeah.
Okay.
Yeah.
Okay. Let's thank the speaker again. So if you have more questions, you can discuss offline.